Welcome back to the last session of the day. And I believe everyone has got these two handouts. One is the presentation copy, and the other one is the how to index a spot diffraction pattern. And it's specially prepared just only for cubic and for silicon lattice. If you want to use this one for a different crystal, you need to do some more changes, such as in step 3, that interplanar spacing. That's really depending upon only for cubic crystals. If you go for hexagonal or any other crystal system, you need to change that formula. And then in step number 7, in step number 6, the angle determination. That formula changes for different crystal lattice. So as the sample that I'm using in this demo session is the silicon, I have given you this indexing pattern, how to index a cubic crystal. So in this demo, we'll see some of the concepts related to diffraction, and we'll see some of the concepts related to holes and hole lines, and some thickness fringes. And when I say thickness fringes, we need to go for Cbd technique. And I believe in the morning, Dr. Rossi has explained you the concepts behind concepts of these holes and hole lines. And we'll see some little bit about the deviation parameter. And finally, I will be finishing with different variants of Cbd mode. So variants means we are using a spot mode as we use in a Cbd technique, but we alter some parameters, such as in CBIM, that's a convergent beam imaging mode. We leave the specimen in eccentric height, but the electron beam will be over-focused. And if you look into the CBD versus LACBD, here the electron beam will be in focus, but the specimen won't be in eccentric height. The specimen will be raised higher, and we get the diffraction pattern. And we see how different are these three different Cbd patterns: CBD, CBIM, and LACBD, and why we should really use those three different techniques. And of course, in the last slide, I mentioned that to be continued on 18/01, that's on Monday. In the Monday's talk, it's going to be a CBD exclusive talk. So in that talk, I'll be using the diffraction patterns that are acquired in this session. And of course, from using one sample, I can't get all different types of CBD patterns. Here, I will try to show you guys what are the different patterns I can get, but of course, there are many different types, because using CBD means we can get different types, because there are many variants in the technique, just by changing the aperture size, spot size, and the camera length. So many are there, many different types. So we on the different zone axes, and if we change something, we get something different information. And maybe on Monday, we will see how to analyze those information and use the CBD technique for different applications. So starting with this demo session, I believe you guys have seen this slide many times so far. In a couple of these 3 days or something like that, you have seen this cross-section model many times. As you know, the sample, the equipment in the TM, which is placed above the sample, that's gun and condenser lens assembly, that's mainly used for eliminating the sample. And the next important thing, the middle bond, that's objective assembly, and objective assembly, that's mainly used for obtaining first image or first diffraction pattern. It could be selected area or convergent beam diffraction pattern, anything. From the objective lens assembly only, we get it. And finally, the projection assembly, it's mainly used for magnifying whichever the data we get from objective lens assembly. So this is a really very, very simplified look of how we can see a TM in general TM. And so first, I want to get a silicon 110 diffraction pattern. As I said, I'm using the same sample that I had used yesterday for the demo. And so let's begin the demo. And yesterday, as I have mentioned, I'll be using this one on this computer as well as this, two different computers. So unfortunately, I have only two monitors, so I need to flip around from one side to another side. And please, during this demo, if you have any questions, please feel free to ask. And so first thing, what I need to do is I need to open the valve so that there will be an emission on the screen. So and I believe the alignment, TM alignment is good enough. So I don't go into any details of alignment process now. And also I'm using condenser lens aperture 2, CLA1 2, and it's pretty much in the center. If not, I need to align it. So yesterday, if you have remembered the process, I did the same process. So I focus the beam and centered to the optic axis, and I open the beam and I check if it's opening concentrically about the optic axis. And I believe it's very good, but still it can be, do some modifications. So for doing that, I use this panel, that's position. So it's in the center, that's good. And it's opening concentrically about the optic axis. That's perfect. So that's nice. Next, we search for a good region on the sample. For doing that, maybe I will move the sample using the stage. I believe this is a good region here, but the height is not really good. So I need to adjust the height. Here, maybe I use image X. That's image X means I'm obbling the, it's a fine. Yesterday also again, I have mentioned that if you want to adjust the height, I normally do it in two steps. One is coarse and one is fine. Coarse, just blindly move the Z height and good, make it get a nearby position where the contrast is nearly equal. And fine alignment, I obel image X and make sure the image is not moving when I press the image X. So I'll try to do the fine tuning. So I obel using this image X. So the image is moving there. So now I change the height and to make sure that there is no that translation in the image. It's getting worse, so I need to go in the other direction. So I believe that's okay. It's not, if you see the edge, it's not really very bad. It's not moving really bad. So I believe that's okay. I stop wobbling. And also, yesterday I mentioned that whenever you want to do, or whenever you start the TM, it's a good idea to check the rotation center. So I will quickly check that one, whether the rotation center is good or not. For that, I focus the beam a little bit for seeing the effect properly. Then I use the HD Obler, and it looks really very good. So now I'm okay with this one. So I need to, first aim of this demo is I need to show you guys this 110 silicon zone axis. Those fine layers are silicon germanium layer bands, and this is a silicon substrate. Okay, so here it's not in the zone axis, so, and also the camera length is about 100 centimeters, which I get it here. So that's the reason I can't see properly. Now, if I reduce it, maybe I can see properly. And you see here, this is the whole ring, but I will show you proper ring. Now, as it is not exactly in the correct orientation, we see that it's a kind of morning sunrise. So I will try to get it's in the zone axis. So for that, I tilt the sample. So I'm tilting in X direction here. Again, I'm using this tilt control here. And when I use plus X, it's going far away, so which is not good. That looks better. Now I'm using a Y direction. So now I need to look for, I think its value is coming around 1500. So I believe it should be okay. And it's not in the zone, it's not in the optic axis. We believe this is our optic axis. It's a little bit away from the optic axis. So I need to bring this one over here. For that, this diffraction, okay. For understanding this, I need to show you the schematics of the TM again. Once after the diffraction is formed, we are here. And we need to use this projection assembly for moving the diffraction pattern or not. So for doing that, for moving this one to the optic axis, I use the projection assembly, that's a PLA, and make sure it's in the optic axis. And here, for activating the projection lens here, I need to use this one, that deflection unit, PL deflection unit. So the deflection it's moving to the center. That's good. So now we are in zone axis, but we can't see anything there. So for seeing that, I change the gamma. You see these bands. Maybe if I use a good exposure of around 0.5 second, Okay, I don't take any risk, but okay, I'll start with 0.1, and I get something there, something good image. And here we see, because the difference between this one and this one is the acquisition time here. You see here, for viewing, we are using 0.1, 2, 3, 4, 5. So 1, 2, 3, 3 zeros and 5. And here we have 0.01. So that's the reason we are here. We are able to see the lines. These lines, I believe by this time you would have known these are called Kikuchi lines. Now I'm in zone axis. Now I want to show you guys the 110 diffraction pattern. For doing that, I go back to imaging mode again. And that's good. So there, this is a selected area diffraction. So I need to use the selected area aperture. Put the aperture in. Maybe I will be using third largest aperture. So that's okay. I move it to the optic axis. Okay. Now I have selected the region on the image from where I need to get the diffraction pattern. So that's the reason we call this selected area aperture also field limiting aperture as well. So I can't see properly. The reason is the camera length is very low. So for getting something good, I need to increase the camera length. You need to remember, if you are in lower camera length, we see the more details outside the 00 band. That's called, we generally called as holes layers. Holes, if you want to look for, okay, I open the beam just to be on the safe side. If you want to get a good details about these holes, you need to be in a lower camera length. If you want to get good details of zero order level zone, I believe you would know what is zero order level zone in Dr. Rossi's class. If you want to get a Zoll's region, you need to increase the camera length. So something there like that. And when I increase it, it's moving away. So I need to bring it to the optic axis. Here I'm using the PLA. The image quality is not that good. So it will be better if I take an image with a better acquisition time. So it's something like that. It's not really tilted very well, but for this demonstration purpose, it should be fine. But maybe I can go for a little bit higher magnification or higher projection length. And acquire some image. And you believe means you see that the spot is not really very sharp. That's because I have opened the brightness. If I change the brightness, maybe I can get a better spot pattern. Getting bad. Better. So maybe I will change the acquisition time. So that's good, but it's not in exact orientation. I will try to do some modification, but I don't think so better because it won't be, because tilting a sample remotely is always bit tricky. But anyway, here we have in the exact orientation. Okay, I will try actually. I think that should be okay. So if I consider this as a 0, 0, 0 disk spot, it's away from the optic axis, so I want to move here. So that's good. So maybe if I increase a little bit more, it will be much better. So that's good. Here we have 0, 0 disk, and we have some disk, spots here. If I open, change the gamma, we have more. And all these spots are Zoll spots, zero order level zone spots. Now, if you want to index, what is that means? You need to follow this. Here, I have shown you two independent spots, and for doing that, if you can open this handout, you will understand how normally we index a spot diffraction pattern. I draw a line and I measure the distances between the spots. That's the first step. So I believe, out of my experience, I believe this as I believe this as 220, and this band as 002. So as the line is like this, we have the spots here. So we'll see, we'll compare. And I said that as a 00 spot. And I believe this has 002 spots. And we have the intensity profiles here, 1, 2. If I want to measure the distance between here, it's coming about 7.167 of a nanometer. So divided by 2 is 3 point something, and as we are in a reciprocal space, we need to invert it as it's been explained in this slides. So we get it is at 0.27, and 0.27. Yeah, I think in this one you can see that it's 0.2717. So I'm sure my guess is correct. So I can index this one straight away as 002. And again, out of my experience, I believe 90 degrees to that 002 will be 220 spot. So the 90 degree spot is about here. So I think that is 220. But like this prediction, it doesn't work for all the time or all the crystals, or even for this sample, it doesn't work. The reason is simple. If you don't know, if you go for a different zone axis, such as, okay, I need to say one more thing. This zone axis is called high symmetry zone axis because due to that, it has got lower index. Lower, when I say low index, means the zone axis of this crystal is now, the orientation is 110. If you have whenever a lower index, that zone axis can be considered as a high symmetry zone axis. And these kind of high symmetry zone axis are not good for CBD work. That's a defect or it's a defect of a CBD technique, because CBD means it has got a lot of dynamical effects. If you're looking into a high symmetry zone axis, these dynamical effects affects the diffraction patterns, and it makes things really very complicated. So always, when you're working on CBD technique, we need to go for high index zone axis. When I say high index, the zone axis will be low symmetry. So it's a opposite. High index, low symmetry, low index, high symmetry. That one you need to remember about it. And also, in the presentation, I have shown you, unfortunately, I have given you the black and white presentation, but here, the 002 is shown with yellow spot here. I don't know whether you can recognize it or not. And 220 is shown as a white spot. The reason is this 002 is appearing due to double diffraction process, and in silicon, this 002 is forbidden reflection. But even though if it is a forbidden reflection, we are seeing here in this diffraction pattern. The reason is simple. It's due to dynamical effects. And I don't know how much time I will be having to explain you guys how to index a cubic diffraction pattern. I wish you will be going through, but if I finish what I want to show you guys today, I will come back to this presentation and I'll explain you how to do it. But if I can't, it's very simple. It's really explained details step by step. I believe you can understand after reading it. In case if you can't understand, please feel free to ask. So next, after this, Kikuchi Map. Again, this Kikuchi Map you have seen already. If not, here we have the Kikuchi Map. The Kikuchi Map, it's visible in both selected area and the CBD mode. But if the electron probe is focused, the visibility of these lines will be much better. And also the visibility of these lines is very much related to the thickness of the sample. So if you go for a thicker region, we see the contrast of these lines much better. If you go for a very very thin region, the visibility will become really very bad. So now I think it's a good time I should move on to CBD mode. So let's see how the beam is in the TM mode. It looks better, but there is an aperture. I need to take it off. In the CBD mode, we don't require any apertures. And because it's a focused beam, we focus the beam exactly on the sample and we get the diffraction pattern. So now for changing to the CBD mode, it's really simple. Adjust the illumination, change the illumination to CBD mode. Click it here. It's changed. And one more thing here, I need to show you guys here. The spot size is 1, alpha angle is 3 when I'm in TM mode. When I go to CBD mode, the spot size is precisely mentioned it as 2.4 nanometer, because when you're in TM mode, the beam is parallel. So the manufacturers just say it's spot size 1 or 2 or 3. They can't explicitly mention the size of the spot when you're in TM mode. But when you're in Cbd mode, it is possible to mention 2.4 nanometers as 2.4. However, when I say this 2.4, it may or may not be 2.4. The reasons are too many, because the spot size, if you measure it on a vacuum, it will be 2.4. As this spot goes from, travels from top of the sample to the bottom of the sample, the spot size changes. How? I will explain you on Monday in my Monday's talk. So now we are in Cbd mode. You can see, of course, I can get a selected Kikuchi map in this mode as well. So for getting the map here in this mode, it's simple. Just I focus it, something like that, and press. Of course, we can't see the Kikuchi map very good. The reason is we are in a very high camera length. So I change the camera length, and I move the sample. I mean, when I change the camera length, I need to change the projector length because it's going away from the optic axis. So for doing that, I need to use the PLA alignment, and I move it to the back, bring it back to the optic axis. That's my optic axis. And you see there, already you're able to see more details in the disk, but because of the diffraction disks are overlapping on each other, the details are not really very visible, and I'm saturating the camera, which is not a good idea. So I go for a lower camera length, and I will show you the Kikuchi map. So one more problem here is always the CBD technique needs to be operated in a focused spot mode. But here, as I'm using the CCD, I'm a little bit scared because of it can damage the CCD. So if I focus the beam to very big, I mean very sharp, it can easily damage the screen. So, but I'll make it quicker. So something there, something is good. Now, of course, okay, that's not good. I need to increase the camera length a little bit higher so that we can see some details inside the disk. think that is a good place there. Yep, that's a good image. Here, we see the good lines. These are called, as you know, Kikuchi lines. This is a central transmitted disk, and I said this is our 002, and this is our 220. And using this, we can construct our own Kikuchi maps, or if you have any electron microscopy softwares, we can easily simulate your maps. And these maps, I think I have shown you in my second slide. I have shown you in my second slide. Because when you're working on Cbd technique, we need to go for different zone axes, and in one zone axis we get some kind of information, and in other zone axis we get some kind of information. We need to correlate all those informations, and we need to understand depending upon the application which we want. So if you see here, this zone axis 011, the one which we are now, if I go along this 400, I get 012. 012 is low symmetry zone axis. The reason why I said low symmetry means we have only two bands, three bands, 1, 2, 3, are intersecting. So this band is good if you want to see some details inside the 00 disk. And if you go to 001 orientation, it's a high symmetry zone axis, and because we have many bands. Of course, I haven't drawn all the bands here. I have drawn only the major bands here. Apart from these major bands, we have minor bands as well. So we have many bands in this orientation, and it's very hard to do some kind of analysis. But of course, this zone axis as well, it's useful depending upon the application. So I want to show you guys the holes, zones, holes, and holes lines. In this particular 011 orientation, I believe it's a bit hard. I will try, but the appearance of this holes and holes ring, it won't be that good because it's a high symmetry zone axis, but I will try. Okay, but in this orientation, I can't see the ring here. The reason is in high symmetry zone axis, normally, it's not the conditional, but normally the size of this holes ring will be much bigger. So it's a bit hard, but I believe here we can see something here. Maybe if I increase the acquisition time, I can see something there. Okay. Yeah. If you can see properly here, this is called false ring. That's first order Levozone ring. And this region is called zones. That's zero order Levozone ring region. But apart from that first order Levozone ring, I can't see any other details here properly. And even the first order Levozone ring as well is not really good. So if I go to a high index zone axis, high index means low symmetry. If I go to a high index zone axis, I can see these details much better. So we'll try to go to the different high index zone axis and see. So just I'm increasing the acquisition for saving this CCD, protecting the CCD. So I'm just tilting it along this orientation, along this red line. As I said, this is our 002 line. So it's going wrong way. I need to use the other way. Yeah, I think you see here, this is called whole ring, but as it's not really exactly located inside the zone axis, I can't show you the properly, but I will try to locate inside the zone axis. It's a total mess. I can't see anything there because I'm in really very low camera length. I need to increase the camera length now. Yeah, I think this is a good zone axis to show you many details here. Yep. So we need, means, okay, by this time you would have been, at least if you're observing carefully how I'm operating here, we have, okay, one thing is I need to, in the microscope, I need to change camera length, exposure, so camera length and which zone axis, all those stuff. But on the software itself, I'm trying to fiddle around this acquisition time, exposure time, and I'm getting some kind of different details. So if I overexpose the CCD, I get good details outside the Zoll's region. This is the Zoll's region. Outside the Zoll's region is this one, Folds region. So the tip here is, if you want to get a good outer region details, I shouldn't say that, but try to be a little bit saturate the camera and get it, but be careful. You can't, I mean, there is a limit for saturating the camera. Here, I'm up to the limit. If I go beyond that, I'm easily damage the camera. So there is a particular, maybe if you use a lower spot size, say 1 nanometer or 0.5 nanometer, the intensity will be much reduced. During that time, you can use higher exposure and get very good details here. And those details are useful if you are working on an unknown crystal. So say you are working on a new crystal which we don't know, and you haven't done any XRD on that. If you want to understand what is the lattice type, you need to have these details. Based on that, you can say what is the lattice type. So we have a lot of details when you're working on CBD mode. It's all depend upon how you get it. So always when you're working on CBD technique, you need to have many, many pictures. And so now in this orientation, I can see some good outer region details, but I can't see anything here because it's really very low camera length. So I'll try to increase the camera length here. Okay. And I will try to center it using the PLA. This disk, when you are in 0, 1, 1 orientation, we can't see this disk properly because it is a high symmetry zone axis. Once when you have moved away from 0, 1, 1 zone axis, we are able to see these details because this is a low symmetry zone axis. So when I acquire an image here, well, it's too high, but it's useful. Yeah, this is what I want to show you guys. This ring and 1, 2, first order Levurson ring, second order Levurson line. And we have, it's a kind of line, straight line here. So for that, I need to take one more picture with a different camera lens. Now we have really good lines, but okay. Here we see the disk with the lines inside the disk. These lines are called holes lines. And holes lines. These lines are called holes lines. The region outside this disk is called zero order Levurson disk. And the region outside the Zoll's region is called holes region. There is a difference between the holes lines and holes region. Holes lines are seen inside the Zoll's disk. Holes region are seen outside the Zoll's disk. So there is a difference between holes ring and holes lines. You need to understand what is it. And these fine lines, they are directly related to the crystal lattice, and these, maybe if I increase a little bit bigger, higher, I get a better view of the lines. Okay, that's it. I can't go beyond this. So that's it. If you see these lines here, or maybe if I can increase the acquisition time, I can make it better. So, okay, see? It should be, we need to know what is the good acquisition time. So, always when you're working with Cbd technique, we need to try with different acquisition times, different thicknesses, different zone axes, different camera length. So there are many variants. So you need to try, and also depend upon your experiment, what you want to get from the CBD experiment. So these lines are black lines. Here, the lines here are white lines. These are called deficiency hole lines. These are called excess hole lines. These lines are as related directly to the crystal lattice. These lines are very useful for understanding the accelerating voltage. Means here in the remote desktop, means the computer, we said that the accelerating voltage is 200 kV. But if you, in general, even though it is saying 200 kV, it won't be at 200 kV. It should be, there will be little bit fluctuation. The fluctuation can be about 100 volts, 1000 volts. And those details are very, very important if you're working on strain analysis. These lines are dependent on, as I said, these lines are related based on this crystal lattice and also based upon this accelerating voltage. We need to calibrate these lines. What is the exact accelerating voltage of your experiment on that day? And further, you need to understand the strain using these lines. And during my Monday's presentation, I'll try to show you how they are related, how these lines are related to accelerating voltage and crystal lattice. That's a strain analysis. I'll show you this one. So now, as I am here in this point, I think it's a better idea if I take three different, if I show you the variant techniques of LACBD, CBD technique, it will be much better. After finishing that, I can go to thickness fringes, deviation parameter effects. So, because this zone axis is good, very good zone axis, the reason why I'm saying this zone axis is good, I know from when I'm working on the image, the silicon germanium bands are parallel to this line, this red line. So this zone axis has got both the hole signs that are oriented parallel to the zone axis and perpendicular to the silicon germanium layers. So I can show you some interesting details now. So I don't want to change and click around till the sample now. I will try to show you the variant techniques of CBD. First, starting with CBIM, CBD versus CBIM. CBIM is convergent beam imaging technique. So this micrograph is CBD technique. The one which we have acquired, I'm showing here, is acquired using CBD technique. Now I will try to acquire using CBIM. If you have seen in your handouts, in CBIM technique, the sample is in eccentric height, but this is the electron beam. Electron beam is over focused, and we acquire the image. So I will try to establish this condition in the TM, and I try to acquire the image. So going back to, so that's my spot, and I put it back onto the optic axis. So here, what do you understand if I change this brightness knob here? When it is something like this, what do you think? And if I'm something like this, what do you think? Here, I'm changing the brightness knob. If I'm in a very focused spot, it's exactly focused on the top of the sample. If I open the knob, it's opening, it's over focusing the sample. That's what I want to show you guys. So convergent beam imaging is just open the sample beam and acquire a good image. So that's good. And I try to open the image. So if you compare with this one and this one, okay. Okay. This photograph was taken using CBED technique, and this photograph was taken using CBIM technique. The difference between these two techniques is I changed the illumination in both the techniques. Here, I focus the beam and I acquire the image. Here, I over focus the beam and I acquire the image. Due to that, here, as I focus the beam here, I get good disk pattern here. But here, as I over focus the image, I get the micrograph filled with hole lines. So this technique is good. Here we don't see any details here. It's black here. But here we have some other details here. So, and we are working this one in imaging mode. So this technique is particularly useful if you have a nanoparticle and how these Holz lines, these faint Holz lines will be affected if you acquire from your nanoparticle. I have an example in my Monday's class. I will try to show you how these Holz lines affect if there is a nanoparticle. It's really very straightforward to see how these Holz lines move or translate or split or what happens to them if you are taken from a exact one single nanoparticle. So I think, but unfortunately, apart from that good analysis, the visibility of these Holz lines, it's really very bad comparison to this one. So this technique is more for understanding how your Holz lines behave just within fraction of seconds. But here we don't have here the information here, but due to here we have a sharp Holz lines. These Holz lines are really very good if you are doing any quantitative analysis. You're quantifying these Holz lines, or because as I said, these lines are as related to the crystal lattice. These are very sensitive for any strain fields or accelerating voltages or any defects in your sample. And it's as the visibility is really very good, here the quantification is much easier compared to here. So if you want to quantify, use this technique. If you want to visually see just like that how the Holz lines are behaving, use this technique. And there is one more technique called LACBED technique. Here, what we do here, we focus the beam exactly same at the eccentric height, but the sample is not at eccentric height. The sample is raised a little bit higher and we acquire it. So what is the advantage of doing that way? We'll see. So here in this orientation, I focus the beam exactly on the sample. Now I change the height. Just increase the height. Okay, so I increase the height small bit. Now I use a selected area aperture. It's off. You see, this is a central disk and it's off. I need to correct that one. So it's going away. That's good. Perfect. It's because a little bit off. I'll try to bring it into the center using the PLA controls. Yeah, that's good. So here, this image was taken using a CBD technique, and this image was taken using LACBD technique. You find any difference between these two images? The contrast of these lines is much better when you're using this LACBD technique. And here, the contrast is not that great compared to this one. So, if you want to see good contrast of these Holz lines, use this technique. And Of course, everyone wants to see a good contrast in CBD hole lines, but if you are using this technique, the illumination on the sample is from here to here. But here we use a spot mode, and the spot size is dependent upon the TM sample. But here the illumination is really very high. So if you are working on the strain analysis, we need to get strain details from really very small regions, say 1 nanometer or 2 nanometers or something like that. During that time, if you use this LSCBD technique, it's not really very good because we change the illumination on the sample, and the beam is illuminating this much distance, and we are getting this information. We don't want only from 1 nanometer of sample, 1 nanometer region. So during that time, CBD is very good. But this technique comes dominant when you're working on defects. It means for understanding the defects, because I don't have any defects in this sample, but if there is any defects, there will be a splitting, the breaking of the hole signs. And those, for understanding that, based on the breaking of these hole signs, it is easy to understand the Berger vectors. So for that case, this technique is really very good. So depending upon your experimental condition, we go for different techniques. Next, I think I have another 10 or 15 minutes. I want to finish a little bit quicker because yesterday there was some kind of confusion because as the bus leaves by 5:30. So I want to finish maybe by 5:20 or something like that. So I need to show you guys thickness fringes, deviation parameter. These are the two things I need to show you. And for quantification of these thickness fringes, I will discuss more on my Monday's talk. So now I will go back to the place where I was, and I open the selected area aperture. There is no aperture. There is no aperture. Okay, there is no aperture. It's not in a really good height, so I change the height and I make it to the eccentric height position. So here, for determining the thickness, yesterday class I think I told that if you use a contamination, if you focus the beam on your sample and leave the sample to build up a contamination, it will grow on the top and bottom of the surface, and you tilt the sample, you measure the thickness. I mentioned about that, but I strongly recommend you not to do that way because you're destroying your sample. So if you want to understand the thickness, the best way is CBD technique. I need to warn you guys, if you're measuring a thickness of greater than 50 nanometers or 40 nanometers or something like that. If you're going to measure lower than that, you can use yields technique. So for lower range, use the yields. For higher range, use the CBD. So that's the thing, but don't use the contamination method. And here, for understanding this thickness, we go to two-beam condition. Two-beam means one transmitted beam, one diffracted beam. The reason why we go to two-beam is simple. It's really easy to understand in two-beam case. If you have many beams in your orientation, the calculation will become really very complicated, and you need to calculate and consider all the diffracted beams into your calculations. So it's simple if you go to a two-beam case and understand the thickness fringes. So for going to a two-beam case, it's simple, but this orientation, okay. So I tilt it to in such a way, I tilt the sample in such a way that it has only two beams. Of course, if you want to change the convergence, you need to change the objective aperture. But if I change the objective aperture, I need to align it, and I don't have that much time. So I change by changing the focusing conditions. I'm changing the convergence, which is not a good way all the time. I go a little bit away from the zone axis so that I can see at least some good fringes. But, and also I need to change, if I am in really very thin region, I can't get any thickness fringes. I need to see where exactly I am. So I believe it's really very thin region. And also you need to remember that if you go for a very thick region, the appearance of the whole thing also is enhanced. And the height is not good. It's too thick. Still, it's not really good, but I will try to tilt the sample a little bit away from the zone axis and see if there is any improvement. Okay. Let me use a smaller condenser aperture because I'm using a condenser lens aperture 2. It's too big. The discs are overlapping, so I'll use a bigger one, a smaller one. So That's a condenser aperture size 3. I need to align it quickly. So it's not really good, but so that looks good. Okay. The camera lens is not really good, so I need to increase it further. Okay. I think the sample is too thick. Okay, I think the sample is too thick or too thin, whichever the reason. I can't see the thickness fringes really very good. So I believe it's too thin, I guess. I'll give it a try once again, and if I can't, it's really simple. Just fill the sample to a tubing case, and you can easily observe the thickness fringes. And based on the thickness fringes, it's really, maybe on Monday's talk, I will discuss how to quantify those thickness fringes. Okay. And measuring the thickness using this Cbd technique is really simple. Unfortunately now I don't know why it's not coming, but and also it's the most fundamental application of this technique. No. Okay, I will leave it like that, but it's really very simple. Understanding these thickness fringes, you need to tilt the sample to a tubing case, and if the sample thickness is less than 50 nanometers or that, it's very hard to see the fringes. So in that situation, yields is the best case. And one more last thing before leaving is I want to say you guys is deviation parameter. In the morning, Andreas told that this parameter as excitation error. So this parameter is also called as excitation error. And here in the image, you can see that even though the evol sphere is far away from the lattice point, we get a spot here. So this point is much easily seen here in the CBD disk. The reason is if you have consider this X-ray diffraction, if the evol sphere is away from the lattice point, the reciprocal lattice point, you don't get any signal. But however, it's not the case in electron diffraction, because this lattice, you see here, there's a small line here. That is because of the electron diffraction. The size of this line is dependent upon the extinction distance of your crystal. And even though the evol sphere is a little bit away, we see some spot or with a really very low contrast. So this effect we can see in CBD mode very good, as shown here. Maybe I can show you quickly. So in this case, this is the Kikuchi line. Even though we are not exactly on the thing, the evol sphere is not exactly touching, we are able to get some intensity here. This is due to the deviation parameter, and that's really very important when you're working on electron diffraction. That's it. That's what I want to say you. And if you have any questions, please feel free to ask. Thank you.